Welcome everybody to a special treat from Canada. I'm delighted to introduce Dr. Patrick Malenfant from the National Research Council Canada, and he will tell us a bit about R2R printed carbon nanotube TFT sheets. Patrick, the stage is yours. Have fun.
Great, thank you, Christoph, and thank you and congratulations to Kasia and the whole team for putting together such a wonderful event, and looking forward to the remainder of the year and the other events forthcoming. Today I'll be presenting some research in the area of carbon nanotube materials development for printed electronics. It is a collaboration with Professor Zhao at SKKU in Korea. NRC is largely on the materials development side. And of course, Professor Zhao is a world-known expert in roll-to-roll printing of electronics. So the talk is basically divided into two parts. We'll delve into what are semiconducting single-wall carbon nanotubes and why you should find them interesting. We'll discuss a little bit how they're purified and assessed, and then we'll discuss a little bit about their use in inkjet and roll-to-roll printed thin film transistors. Now, for those of you who are not familiar with single-wall carbon nanotubes, they are basically a single sheet of graphene folded upon itself. When they are synthesized, they actually typically come as a mixture of approximately 70% semiconducting carbon nanotubes, 30% metallic. So in order to use the material as a semiconducting channel material in a transistor, one has to devise ways of removing metallic tubes. And while there's some nice research being done on synthesizing exclusively semiconducting tubes, none of those have really been demonstrated to work at scale that would be compatible with formulating inks and using them in printable electronics. And so some early work in the 2000s demonstrated selective dispersions with DNA, but it wasn't until a little bit later that people realized that you could use conjugated polymers to do selective dispersions of semiconducting single-wall carbon nanotubes. And it's quite interesting. A variety of polymers can be used, and one can actually get chirality selectivity, diameter selectivity. And so again, when you think about a semiconducting single-wall carbon nanotube, you want to think of it as a population of chiralities, which is effectively the graphene sheet folded into a cylinder, but can be done at different angles. And so that gives you different chiralities and different diameters. And then people have been exploring quite a bit in the last 10 years how to improve the process for the purification. And there are various ways of doing this, but for today, I'll only focus on using the conjugated polymer approach, which is the one that we have been focusing on. It's important because you're able to do this in a non-aqueous environment, so you don't introduce any ionic species, metallic ionic species, into the sample. And so it is a selective dispersion, typically done in an aromatic solvent, in which the polymer will be sonicated in a dispersion of tubes, most often toluene, and then simple centrifugation can be used, where the metallic tubes will be crashing out first and can be precipitated to the bottom, whereas you will get an enriched fraction of semiconducting carbon nanotubes in the supernatant, which is the top of the solution. And then one can do this repeatedly. You can repeatedly take the sediment and redisperse it in polymer and continue to extract selectively semiconducting carbon nanotubes. Now, we don't really have time to really get into our beliefs on the mechanism, but the fact that it is a system in which highly polarizable metallic tubes will be attracted to charges, and that in the presence of water and oxygen, semiconducting carbon nanotubes will be a little bit doped, a little bit p-doped. So that leads to an attractive force. So naturally what that means though is we'll be taking down semiconductor